All right, so today we're going to define vapor pressure, what that means, and determine situations and explain cavitation. All right, so this homework that is posted, we'll go through it here in a little while, covers some of the stuff we covered last time. So you'll have a an Excel plot with mock numbers that I want you to do. Okay, so again, practice you with Excel and get comfortable with that. And then it'll talk about vapor pressure, cavitation, and then there'll be a problem on viscosity. Okay, so we'll cover that in next class. So you should be able to do a good chunk of the homework already, especially after today. All right, so if you want to get started on that, you can over the weekend to get kind of ahead of things. But last class we talked about density, specific gravity, specific weight. What else did we talk about? Mach numbers, speed of sound. Okay, so those are all generic properties that we use and talk about throughout the whole fluids. So if you ever hear fluids, those are the main concepts. Okay, then we want to talk about vapor pressure and cavitation. These are concepts that are used heavily in, like, when you're dealing with boiling, a little bit in thermo, and you're dealing with propulsion systems, okay? And also when you have pumps and you turn them on, sometimes they cavitate, and you want to know what that is and how to avoid it, okay? So let's first draw a little sketch here. Here's a room, and here's a table, and here's a cup of water. Okay, so you could have it in this room, and there's no one else in here. So the room is completely dry. Oh, and say we're at standard conditions. So around 20 degrees C, the temperature, and the pressure, let's say, is 1 atmosphere. Okay, in the room. And let's say the water here, so the temperature of the water is 20 degrees C. And the vapor pressure in the room is 2.34 kilopascals. So the room is at 20, the water is at 20, the pressure is 1 atmosphere, and this vapor pressure is of the air in the room, okay? So vapor pressure, all it is telling you how much water vapor the air can hold, okay? And it's all based on temperature. So, it's humid out right now, right? That means if it's really humid, we have higher temperatures. So higher temperature, the air can hold more water in the terms of a gas, which is the vapor. Okay, when it's cold out, it's dry, right? You have the static on your clothes. It's because the air can't hold as much water vapor anymore. Okay, so anytime you want to know what the vapor pressure is of water, you just have to know the temperature that you're looking at. And those tables are in your book, in the back of the book, or they're in the chapter. They're sometimes in both places, okay? So depending on this temperature, you'll know how much water vapor the air can hold. Think of it as like a sponge, and it's trying to soak it up. So what's going to happen to this water in this can if the room is completely dry? Well, we zoom into this, some of that liquid water will convert into vapor. And the water liquid level will drop because everything wants to be in equilibrium. All right? If it's completely dry, it needs to absorb some water, and it does that from the liquid top level here. Okay? So now we have an equilibrium between liquid and vapor now. So depending on how much the air can hold is how much liquid's going to evaporate and turn into a vapor. All right, so this happens all the time. All the time. okay? So we look at graphs like this. So if we look at the vapor pressure as a function of temperature, think of it as cold to hot, you can hold more water in the terms of vapor or gas. So on this side, we're going to talk about this, on the left side of that curve, whoops, let me move that down, this is a liquid. And on this right side is a gas. So there's two ways that we can actually get water to turn into a vapor. Okay? The first way is at constant pressure. So think about when you boil your water to bake noodles or whatever. The pressure in your room or wherever you're cooking is at atmospheric pressure. It's at one pressure. And what do you do to make the water boil? What do you have to do? Increase the temperature. Okay, so constant pressure, increase temperature. So that looks like this on a graph. So 100 degrees C. So here, this line represents what you do when you make and boil water in your house. You're at constant pressure, but you increase the temperature, and then boom, at that point, what's starting to form in the water? You ever see it from the bottom going up? Bubbles, because it's converting it, it's boiling, it's turning it into a vapor. So there's a difference between boiling and evaporation. So boiling, you will see air bubbles all over the place in the liquid. Okay? Evaporation only occurs at the surface of this water liquid vapor phase. Okay? So just remember those differences. Okay? If you're at a lower pressure, what happens? You can boil at lower temperatures, yes. Okay? So that's why a lot of the times, if you go up elevation, you drop the pressure, right? Or they have a pressure cooker. Okay, you have a lower pressure, you can boil at a lower temperature. Pretty cool, right? This is what we observe all the time. So the first way, constant pressure, increased temperature. The second way is, what do you think? What's the reverse of that? Constant temperature, but decrease the pressure. Yep. So I'm going to draw this again, so you have this in your notes. So if we're here, we're at one constant temperature, and we drop the pressure, boom, we start getting air bubbles. And then boom, it's all vapor underneath it. All right? So there are two ways you can make liquid change into a vapor. Keeping the pressure constant, increasing the temperature, or keeping the temperature constant but dropping the pressure. So this second case, where you drop the pressure, that occurs a lot when if you're riding in a boat and all of a sudden you crank on the gas and the prop spins really fast. The pressure around the prop in certain spots drops rapidly. Okay, it's at the same temperature, but it drops. And then what happens? We get air bubbles around the prop. And they're at a lower pressure. So if the liquid is at higher pressure, what is that? Do you know kind of, we haven't really talked too much about pressure. You hopefully have an idea if you have high pressure and then low pressure, which way is it going to go? Inflow. Yeah, it's going to go in. So when you put your gas pedal going on your prop it drops the pressure, certain areas around forms into air bubbles, then they implode because they're at lower pressures. And it's the little implosions, and that's what happens. You get issues with the prop. So as it's spinning, it creates these air bubbles because they're creating low pressure, and they're actually imploding. And they're causing little basically explosions or implosions as they're going in. And those are really close to the metal, and it causes damage because it's a high pressure wave hitting that. Okay? This also occurs in pumps in certain situations because a pump has a propeller. And it's spinning around, and it could create low pressure and cause that. So sometimes you need to do is you need to monitor your pumps to make sure that doesn't happen, or if it does happen, figure out how to fix it. Okay? And future down the road, you'll see when you take like an engineering economics, if you have this issue, you need to look at 1, 2, 3, 4 different solutions to fix it and what's the cheapest way. All right, so you'll see down the road how you can then use this project to figure out an economic analysis. Okay. I'll post this video so you can watch the whole thing. Let's see here. So here is, oops, I didn't mean to do that. I didn't want to do that. So again, the difference between boiling and evaporation is boiling. You start seeing bubbles all over the place. Well, evaporation only occurs at the top of the water to air interface. Sometimes when who cracks their knuckles? Anybody crack their knuckles? All right, a few of you. Okay. Basically, what's happening is you're creating like a little cavitation issue. Okay. You're pushing it in. It changes the pressure, drops it, expands some stuff in there, and creates these little implosions kind of thing. Okay. And I've been doing it all my life, and I haven't had big knuckles. I think they've done a lot of research on that. It hasn't affected me. So, so how do we determine if there's a situation that will occur for cavitation? Well, let's do a quick problem right here. And you're going to have a very similar problem on the homework. So this is the table that's in the Senegal book, but the Mott book also has these tables. They're in the back. And they are given what they say saturation or vapor pressure at various temperatures. All right, and temperatures on the left, and the saturation pressure or the vapor pressure is on the right. Okay, so again, the saturation pressure, vapor pressure is how much the air can hold at or in the water vapor phase. So here we have a prop, and it's in 20 degrees of water, and the tips of the prop, we've noticed that the pressure drops to 2 kilopascals. So will there be cavitation? So what is the vapor pressure at 20 degrees? Yeah, so the vapor pressure at 20 degrees C is 2.34 kilopascals. And since our pressure that we've noticed is lower than that, yes, danger. There will be cavitation. And later on, and next week, we'll talk about pressure and how you can measure pressure. Okay.